Guys, come with the sticky ones. It's a pipe bomb.
What? Yeah. I saw Michelle in the parking lot. Was like, hey, what do you do for lunch? So I just went over to find it.
Oh, okay.
Someone made it.
I mean, it wasn't just me, but what?
Sour patch encasing a warhead.
To get them, I understand. Like you got
A war?
once you get them, then.
Surprise! Only need 3 hours.
Okay, we put in 2 hours of work tonight.
I'm for it.
3-2 is like.
Are you doing thermo in material science? Like
Saturday. Twice that.
That's where
we'll be
the
done.
balance is, put back. But if that's the thing that's keeping you from getting to that point, then it's Friday. All right, let's talk about materials.
Yay! Let's get down to business.
Okay, so this is before we actually start, let's have a brief discussion on the exam, which is currently scheduled for either Friday and Monday, or just Monday, depending on whether we want to do the 2 hours out of class, material science.
For this Friday, like next class?
Like the next class and then Monday after that. We're all
Tuesday.
So,
Monday, because I will not be here.
I'm assuming that means we'd rather do it as a 2-hour exam next week. Is that correct?
Yes, way late.
Yeah.
Yeah, you can do it Tuesday.
Tuesday.
No, not Wednesday. Not Wednesday.
That's next Thursday?
Next Friday.
I'm doing after fall break, is that correct?
Yes, try that and see what happens. So next Tuesday then? Are we okay with next Tuesday? Same deal as thermo, and for those of you who weren't in thermo, the same deal as statics, because everybody's, you had statics last year. But basically, okay, so the big deal is you have to email me with what time you're going to be taking the exam, just like it is in thermo tomorrow, for those of you who haven't emailed me about what time you're taking your thermo exam.
It's 4 o'clock now.
And you have to start sometime between 8 and 5. And you have 2 hours that you're self-governed on the 2 hours, because I'm going to be able
What
to
hours are
say
you going to be?
We have 2 hours?
2 hours. What's that?
How late are you going to be here? 7.
8 to 5.
Oh, wait.
So you can start,
So
you can
if we
start
at 5, you won't be here.
Right, exactly. That's the point. So the idea is if you take it at 5, that's your call, but then you don't have
Really
any
call
resources.
yourself then? No, we can break into his office and let him answer.
Yeah. It's on video. Just so we're clear, that's on video. So
Well, if you have a broken window in your office in the next couple of days, then
I'm coming after you, Jason. All right. So anyway, so Tuesday then,
Yes.
and then we'll start the next chunk of material on Wednesday.
we have class Friday and Monday?
Which means that we can, then it's going to be the same deal. So Friday will be for you guys to ask questions about your homework, and then Monday I'll be available during this time slot for you to ask questions about your homework. But I'm not scheduling class on Monday. I will be in this room on Friday if anybody has questions about their homework.
Would it be possible to flip those days and have Monday be a question day instead of Friday?
Sure. You want to vote?
I'll vote for that.
How many people vote for Monday as the question day?
Yeah.
Because everybody wants to get their homework done over the weekend. Okay.
Clayton can't be here, so.
What's that?
Clayton won't
I
be here.
can't be here. I'm
Well, my son's not going to be here either, but I figured I would be showing bias if I made any gesture in that regard. So since you guys voted, that'll be all right. Okay, so then I will be available on Friday during this time slot, but then on Monday during this time slot, we'll actually have a chance to go over homework questions. Does that make sense? Everybody okay with that? All right.
Your beard's turning white.
No, it's not.
Look like mine.
It is extremely blonde.
It's going to look like mine soon.
Silvery vacuum.
I don't think my head will ever look like yours. All right. Thermal properties. So this is the last piece we've got. Thermal properties. Yes, this is materials. We're talking about thermal properties. And the nice thing about it is for those, what, 11 of you? 10 of you that are in thermodynamics? Who's not in thermodynamics? You're not, you're not, you're not. Yeah, that's true, you're not. All right, for those of you not in thermodynamics, this will be new. For those of you in thermodynamics, you're like, all right. Thermal properties of materials. The one that what do you think is going to be the first thermal property I'm going to start with?
Hot.
The three states or phases.
Thermal property. An inherent property of material that is thermal in nature. No, I'm not going to start with its melting point.
Density. You are my destiny.
You know, you are my density.
I know.
Anyway, no. Apparently we haven't been preparing for our thermodynamics exam quite
There's
well.
like a million different
Specific heat capacity.
Yes.
I literally have 12 hours and, no, not less than more than that probably.
Depending on
I have 20.
Specific heat capacity.
What's the arm make it from like there to here?
So for materials, now for those of you in thermo, okay, we know that if we have a constant heat, if we assume this to be a constant, we know that it actually does vary with temperature, but over some finite temperature range, we can assume it's a constant. We know that delta U, the change in the internal energy, is equal to mc delta T. The change in the internal energy is equal to the mass times this material property, specific heat capacity, times the change in temperature. But for solid materials, we know that the work is equal to 0 because it doesn't change volumes. And a solid material doesn't expand and contract as you do work, or as you push on it. So delta U is equal to Q is equal to MC delta T. So what you see in the material science textbook is going to be Q equals MC delta T.
Because the solid material can't have the work.
Because a solid material doesn't expand under pressure significantly. Q is the heat that you add to the material, M is mass, C is specific heat capacity material property, and delta T. And there's actually two specific heat capacities. Cp is at constant pressure. And there's Cv, which is at constant volume. So it's how they're measured.
What do you mean by at constant pressure and at constant volume?
They're measured at constant pressure and constant volume.
Yeah, but you measure it at one instant. It by definition has constant pressure and constant volume.
Right, because we're seeing how does U change when the pressure is constant, and how does U change when the volume is constant.
Okay. So could you think of like an example of measuring a CP or
So-
CD?
So we talked about this a little bit earlier. So if you have a rigid tank, and you're trying to measure a rigid container, and you pump heat into it, and you want to see how the internal energy changes the stuff inside the tank, then that's a constant volume process, and so the internal energy is going to change in a certain way as you pump heat into it. However, if I, instead of having a closed tank, I have a piston cylinder assembly, in which this is just floating. I pump heat into that, it's now a constant pressure, because this is free to move up and down, and I'm going to get a different response in terms of how much internal energy is stored when I pump heat into it. Okay? So, but realistically, and again, in solid materials, those two are essentially equal. So we don't make a differentiation. In reality, CP is slightly larger than CV, but we don't make a distinction for solid materials. So this is all we really care about for solid materials. There's just more to it behind the scenes, as those of you in thermodynamics are aware. Okay, that's one thermal property. What's another thermal property that we've also talked about in thermodynamics? Melting point. Nope, we aren't at the melting point yet. I'll just go through them.
There's too many different things.
We talked about thermal
Properties.
expansion.
Oh, sex.
Thermal expansion. Remember we talked about thermal expansion.
Yes.
Okay. Alpha, that's the thermal expansion coefficient, or coefficient of thermal expansion, or CTE. Is 1 over the length PL dt.
I don't think we did talk about thermal expansion.
We haven't talked about it functionally, but we did talk about it in the fact that
Volume.
when you heat it up, the
No, we talked about
bond length increases, and then we talked about the fact that vacancies increase.
yeah, in material science.
Oh, that's in here. Ah, you're right, we haven't talked about it in thermodynamics, sorry. Well, then,
we're right.
okay.
And you thought we were stupid.
You know,
Still might not be wrong.
so that's the differential form.
It's not going to be on the thermal test.
Correct. That's the differential form, and this is the sort of the empirical form of the expression. Change in length is equal to the initial length times alpha times the change in temperature. So this one assumes that alpha is not a function of temperature. You know, that it's so I can go ahead and do the integration directly up here. Okay. And it's derived from that E versus A curve, from the E versus A curve. It's derived from this, a combination of that. And so derived from that plus vacancy formation. So it's a combination of those two characteristics that drive thermal expansion. Let's see here. Okay, third quality. Thermal conductivity. This is from thermodynamics. Where we talk about the rate at which heat flows through something, so we put the dot over the Q, so it's Q over time, is equal to the thermal conductivity, K, times the area through which the heat is transferring, times the thermal gradient dt dx. And in solid materials, this thermal conductivity is pretty much exclusively driven, well, on metals, it's pretty much exclusively driven by electrons.
What does the dot mean?
Q dot means dq dt,
Oh.
the rate. So in metals, or conducting materials, it's about the electrons.
Isn't it negative K dt?
Well, yeah, it depends on how you define your dt dx. I guess it can be. We're not worried so much about, in here, we're not so much worried about the convention that Q into the system is positive, and Q out of the system is negative.
Okay.
Okay.
Oh, we are in thermal, right?
But we are in thermal, yes. So, again, so in metals, this is driven by electron conduction. In other words, since the electrons are free to move, I get the electrons excited, thermally excited. The electrons are the things that have the high kinetic energy. And then they can physically move through the metal, through the Fermi sea. In non-conducting materials, it's lattice vibration. So others, this is associated with lattice vibrations. So in other words, the atoms at the surface start vibrating in their lattice. They push the next one. They pushes the next one, and so on. Yes.
This is slightly unrelated, but you were saying so adding heat energy means that the electrons are more free to move.
No, what it means is the electrons have higher translational kinetic energy. And then those electrons that have high translational kinetic energy are themselves free to move, and when they move, they carry that translational kinetic energy with them, thereby conducting the heat through the material.
Okay.
So,
how does that relate to electrical resistance?
very strongly.
Okay.
So you'll find that there's a strong correlation between thermal conductivity and electrical conductivity in metals.
And as you heat something up, doesn't that increase the resistance?
So you heat, but you heat something up, and it increases the likelihood that those electrons will bump into each other, which limits their mobility through them. So that means, your thermal conductivity may not be constant at all temperatures. Right? K itself may be a function of temperature, so that at high temperatures it is less thermally conductive. Okay. But the process by which thermal conduction occurs is the motion of the electrons. Okay. It's kind of almost like convection in some sense, right? Because it's a fluid. The fluid in this case is the electrons. Yes?
Now, do metals also experience lattice vibrations? It's just that it's
Yeah, they're
mainly...
just not the dominant. The dominant mechanism is the... So if you look at thermal conductivity for, I don't know if I've got a table here. Maybe there's a table in the book. If you look at the thermal conductivity of metals and compare it to non-metals, the metals are just much more highly thermally conductive. What chapter am I on? 7? Yes. Thermal conductivity, metals. 237, 398, 315, right, numbers like that. Ceramics, 5.9, 1.7, 15, 2, 25. Okay. Omaha. Anyway. Okay. So, so everybody got the idea here.
Wait, what's that?
And the things that can impede thermal conductivity, anything that can impede these two activities is going to impede thermal conductivity. So if you've got a substance that is glass, amorphous, instead of like a crystalline ceramic, so if I take quartz, SiO2, right? It's a crystal. We've talked about the crystal structure of quartz in one of the earlier chapters. If instead you have glass, which is an amorphous version of that, so that you don't have this crystal structure, then thermal conductivity is impeded because you don't have this nice lattice structure in order to pass along the vibrations.
So glass is decent, is
A glass of the same material would have a lower thermal conductivity than a ceramic of the same material.
Wait, you can make glass out of materials.
What's that?
You make glass out of materials.
Yeah, you make glass out of different materials, sure.
Let's see.
Anyway, something new every day, right? Okay, so anything that impedes electron motion, so like Joel was talking about, if you've got higher temperature, that higher temperature is going to impede the motion of the electrons and thereby reduce the thermal conductivity. Okay, or if you've got pores or like big agglomerations of vacancies or whatever, obviously it's going to be hard to pass a vibration from one side to the other across this pore. So you have to go around. So you get more a higher thermal or lower thermal conductivity in those cases. Okay, does that make sense? Yes. You're good. You're stretching. Okay. All right. Next, 4. This is not so much a thermal property as it is a thermal phenomenon. Thermal shock. So thermal shock is the interaction of these two pieces. So I've got the coefficient of thermal expansion. That's what that alpha is, the coefficient of thermal expansion, and the thermal conductivity, which is the K piece of this. Right, those are the two material properties. Yes?
You said it was the interaction between thermal expansion and conductivity?
Right. Thermal shock is the product of those two interacting. So the main mechanisms, so imagine if you will, I take a sample of stuff, some kind of stuff, and I heat it up, and then I glue it to a wall at the top and the bottom. So it's hot when I put it in there. And maybe I weld it, maybe it's a piece of steel that's welded, or a piece of glass or something. Okay, it's fixed into place. Then I cool it off. What's going to happen? According to, by thermal expansion, what's going to happen? It's going to want to contract. It's going to want to shrink, right? But I have it constrained at the top. I have a mechanical constraint here. So as it cools, it's going to want to shrink, and I create a stress inside of it that can break it apart. And so if I take a glass window and install it between these two things at a high temperature, it's really hot, and I put it in there, and then I let it cool, it's going to shatter. And so has anybody ever, this is one of the places you can see this, is if you take glasses right out of the dishwasher. Oh, you guys are kids, you don't ever empty the dishwasher. Just saying.
I do dishes by hand.
We do hand washing dishes, not.
Dishwasher.
I need dishwasher.
They do.
Well, yeah, they shatter here. They shatter when you hit the tail.
They what?
They only shatter when you hit the tail. Otherwise, they're like infinitely strong or whatever when you try to smash it with the
Okay.
rod.
Let's see if you can figure out how that works on the basis of understanding a large thermal gradient. Okay, so I take a big chunk of glass or something. Okay, like maybe one of my glasses here, right? I get it hot. Maybe it's been in the oven holding a casserole. And I dunk it in water. All right, so here's the thickness, the thickness of the thing. I dunk it in water. What's going to happen?
It's going to shrink rapidly.
The outside.
The outside what?
The outside surface wants to shrink.
Well, what's it going to do fundamentally first? Before I mean, it's going to cool. Right, the outside surface is going to cool. So if I do a temperature profile, right, the outside surface is going to be a cold temperature, the inside surface is going to be a hot temperature, right? So what happens when the outside gets cold? What happens to anything? Almost anything, when it gets cold? It shrinks. So the outside wants to shrink. Right, so the outside shrinks. Right? But the inside is still hot. So it can't shrink. Right? So what that means is that the outside pulls the inside together, and the inside is in compression. Mocking me?
So if you
Laugh at my picture.
You're mocking me, aren't
If
you?
you stuck it in the shower, that wouldn't happen, because it all cooled at the same time.
No. If I hit it with cold water, if I hit this thing with cold water, the outside, all the outside's gonna
You
get
know what I'm
cold.
saying, like if you put it in the shower though, then you have cold water on the inside and on the outside.
No, this is not, this is like
It's like
a
a
single wall of glass.
Oh, in like the inside.
This is the wall of the glass. Okay, has everybody got that now? Okay. So the outside's gonna shrink, it's gonna squeeze the inside in compression. But the inside's not gonna shrink, and so it's gonna pull the outside in tension. Right?
Right, why is it pulling it that way?
It's pulling it apart.
Because
Because the inside isn't shrinking. The outside wants to shrink, but the inside won't shrink. So the outside tries to shrink, the inside keeps pulling it back apart.
Okay.
So we end up with tension, because the
But-
outside is stretched.
technically though, it's pulling this way. It's pushing as well as pulling, right? I mean,
No, lateral contraction is negligible by comparison to the, lateral contraction is immaterial. What I mainly care about is what's happening at the surface. Right? There would be lateral contraction, so there'd be, if there was a wall of the thing out here, you'd have that same phenomenon on that wall. The point is, the outside is under tension. So what happens when you put glass under tension?
It doesn't do very well.
Why does it break under tension?
It doesn't have a high.
No, no, that's not why. No. What did we talk about? Why is glass particularly a problem under tension? There's no toughness. No, there's something else about glass.
It's got cracks.
It's got cracks. Right? Remember, glass has cracks, right? It's a brittle material. So if it's got cracks, then this little bitty ding on the side, you know, right? The little bitty crack on the side. You can't even see it. It's microscopic. But it amplifies the stress. Remember, sigma max equals 2 sigma square root of C over rho. Remember that expression? So we amplify the stress. So if this is in tension, I'm pulling it apart, creating a tension on those cracks, it shatters. So when I take that glass plate from the oven and put it in cold water in the sink, because the outside shrinks while the inside doesn't, putting the outside under tension, and it pulls that crack open and causes it to propagate and shatter the glass.
We should have video demonstration, like, there's video
Why would that
on
be?
YouTube, like,
There's plenty of
we
these
should
things.
incorporate that, like, the Prince Rupert's.
Yeah, okay, maybe the year that I'm not teaching 34 credit hours, I'll incorporate the videos.
Wow.
Yes.
Dude, take it easy, come on.
Somebody should make a note, okay? I
Yeah, somebody should make a note in your
Suggestions.
notes.
No.
should make a note and send it to me. Suggestions.
For the,
That's right.
course evaluation.
That way-
Hey.
For next year.
Let's put it this way. Erickson is sitting in his underwear watching this video at this point, so he can be the one to write down a note and send it to me. Since a note on every other video, you might as well do it on this one. Okay. Maybe you be constructive this time. I don't know. All right. Anyway, so do you understand what happened there? Do you understand how that happened? The outside cooled, it shrunk, but the inside didn't, so the outside gets pulled apart and shatters.
I'm also still confused about direction of the tension, so is that like the outsides of the glass and then that's the thickness?
The outsides of the glass
Yeah,
shrink in the plane of the glass, right? If I'm looking at the window, it wants to shrink, but the inside keeps it from shrinking, so the inside is essentially pulling apart the outside, while the outside is pulling together the inside, putting the inside under compression and the outside under tension. Still not getting it.
can't
So,
really
so the outside is under tension caused by the inside under compression caused by the outside.
Exactly.
But all the poison in the vessel constantly.
Shut up.
So if we had just a plane of glass and we were looking at it thickness wise,
Yeah.
then there would be tension up and down the glass?
There would be tension pulling the glass apart along the
Okay.
entire surface,
Yeah.
pulling it apart in this way and in this way.
Okay, so it is pulling it apart?
It'll
No.
pull apart in the plane of the glass. This is the glass plate.
Yeah,
This the glass window is really hot. I
Yeah.
throw a bucket of water on it.
uh-huh.
The outside wants to shrink in all directions, right? It wants to
Okay.
shrink.
So why doesn't
But
want to
the-
shrink perpendicular to it?
It does, but I don't care about what happens
Okay.
perpendicular to it, right? Because all I care about is the fact that there's cracks on the surface. The
Okay.
cracks typically aren't on the inside.
Okay,
Right? So the cracks on the surface are the ones that are going to get pulled apart.
I see. Okay,
Okay?
yeah.
All right.
So that's also why you don't put
So-
hot things on granite countertops.
Also, why you don't put hot things on granite countertops. Well, that's part of it anyway.
What's the other part?
Well, you can actually, there's other chemical things, I suppose it could be.
Oh.
Yeah, I don't know, you can burn the, I don't know what else they can bring in countertops. There's materials that could react. Britton, who has his hand above his head, yes.
Nice. So if you did this with a non-brittle material like metal, does that actually harden it?
If I do this with a non-brittle material, well, we're going to actually do it a little differently with the brittle material, we'll talk about that.
you make tempered?
You guys just, let me get to it, all right? Anyway, go ahead.
I was gonna ask, is this highly related on the conductivity of the material?
So right, so that's the point. If we have a low thermal conductivity,
Yeah.
then this is going to be amplified because I'm not going to be able to get that heat from the inside out to the surface, right? If I have a high coefficient of thermal expansion, this is going to be amplified because the outside is going to shrink more. So a high alpha and a small k give me accentuated problems here, okay? And the way that you can actually avoid this happening, one of the ways you can avoid this happening is to make sure that whatever you have doesn't have a lot of porosity in it, right? So there's not a lot of cracks. So you want to use something that is truly a solid material all the way through. So when you talk about Pyrex or Corning ware,
Pirates? Sorry.
those are materials that you're supposed to be able to do this with, right? Because they have very low coefficient of thermal expansion, driven by the fact that actually Corning ware is a mixture of ceramic and glass. So it's a mixture of crystalline and amorphous material. They mix those two together so that they have a very low coefficient of thermal expansion, so that even as I quench this, the outside doesn't shrink that much, so that they can tolerate that. So those materials, Pyrex and Corning ware, have low alpha, small alphas. Okay. Before I get to tempered glass, I got to cover one more thing that we talked about last time, but I want to hit it again for ceramics. And that is, what are we up to, 5? Viscous deformation. Okay, so we have the strain. Remember we plotted, actually last time I think I plotted the modules. Here I'm going to plot the strain. So delta L over L naught as a function of temperature. And I'm still going to have those two temperatures, the glass transition temperature and the melting temperature. What happens as I warm it up is I get a certain amount of strain, thermal strain, stretch. Then I get here, I get a higher amount of strain before it eventually, once it melts, it can't support any strain. What's TG again? Glass transition temperature.
What is this L? L naught.
The initial length, delta L is the change in length, and L naught is the initial length. So I have a single bar that I'm heating up. Okay. So there's this transition that occurs at the glass, at this glassy. When it becomes glassy, the thing undergoes, excuse me, a larger expansion. Right? The alpha is different for the glassy phase than it is for the crystalline phase down here. And if I plot, is there a question there?
Is that supposed to be like a straight line, or is it kind of concave up?
It's supposed to be a straight line. Now, and similarly, if I plot specific volume, that is volume per unit mass, as a function of temperature. So I take it at some above the melting temperature, it's a liquid, right? As I cool it down, what will happen, this will do something like that.
What's that L? Does that mean
Liquid. It just means it's a liquid there. So as I cool it down, it kind of continues to behave like a liquid, even below the melting temperature, in terms of its volume per unit mass. Okay, so in other words, all I'm doing is I'm just stopping the vibrations. So it's essentially a viscous material in here.
So is between TG and 0 flat? Or
No, it's not flat, it's just a lower
slope?
slope. Because it's still cool, right? It's still, this is basically mapping thermal expansion. Volume per unit mass.
TM is the melting point,
And TG is the glass transition temperature.
which, what does that mean physically again?
It means this, actually, is what it
Okay,
means.
it's defined by where that
It's defined by this behavior. So it behaves like a viscous glassy material up here. It behaves like a sort of a nice solid material down here. If I cool it really slowly, I can get it to do this. Where these two are roughly parallel lines. this is crystalline, whereas this is glass. So if I take a ceramic material and cool it very slowly, I give it enough time to reorient itself into an actual crystal. So I take if I melt glass, right, get it to be a liquid, and cool it very slowly, it will form, if it's pure glass, it'll form quartz. But I have to cool it very slowly in order to get it to go from the liquid state right into this crystalline state. And there's a discontinuity in the volume temperature graph, excuse me, because it's actually changing from an amorphous condition to a crystalline condition.
So you basically kind of sit.
Crystals are much more organized.
You kind of sit at the temperature of the melting stages for a while.
Right, so you just basically cool very slowly, right? Okay. But if I cool more rapidly, it'll solidify here in the sense that it's hard now, or it's, it's not liquid or whatever, but it's still viscous. Okay, so it can still deform. Right? It has a viscous strength. It looks like liquid, but I mean it behaves like a liquid, but it has the actual sort of consistency of a solid. So it's not.
So what does that mean? Like Play-Doh?
Yeah, kind of. I mean, like you've seen glass blowers, right?
Right.
Glass blowers are working year-round.
Okay. So it's still a solid, it's not going to drip, but you can still easily manipulate it.
Right.
Kind of like when the wax in a candle is still, you can still poke in it, but it's not going to flow.
Right. Okay. So, what happens then? What would happen if on this sample over here, the one that I quenched, if the outer surface, if the temperature profile were such that this temperature right here was T sub G.
Then the outside would be hard and the inside would be viscous.
Right. So if I quench it such that T sub G is right there, the outside gets hard, but then the inside is still viscous. So as this outside shrinks, the inside viscous stuff is able to flow to accommodate that.
Confused with yourself. Do that again.
Do it again.
No.
Damn.
But do you see what I'm saying? Right? Do you see what I'm saying? This stuff shrinks and puts the inside in compression, but the stuff that's in compression can then flow to relieve that compression. Right? So that after a bit of time, my temperature profile then, or my stress profile, that's the temperature profile, my stress profile then kind of looks like this. Because the inside can accommodate that stress.
So is it actually compressing? Or you said it can flow to relieve itself, but
Right, so it's no longer compressed.
okay.
Where does it flow to though?
It just flows within itself, That's what I said, it just kind of does this. I mean, it flows within itself. Right, it's able to distort. I mean, it
Doesn't it need like a change in block, like
if I blow on a piece of hot glass, right, it deforms. I apply stress and it responds to that stress. So here, if I'm trying to squeeze it, what would actually probably happen is it would squeeze it and get slightly thicker, right, to accommodate that compression. Does that kind of make sense? Okay. And so what I want to do is I want to keep this stuff in the center just above TG while it can flow. Then, once the stuff in the center is right at TG or just above TG, then I quench it further. Now the stuff on the inside cools off, right? Becomes rigid. And in fact, what I end up with, I don't know if I want to use black or red. So if I now slowly cool the inside to room temperature, as this cools, it will shrink. But the stuff on the outside has already been hardened. So what I end up with is a stress profile, I guess I do want to use red. A stress profile that looks like this. So that now, because now the outside is rigid, the inside has flowed, but it's still hot. As I cool the inside now, it shrinks, but the outside that's rigid can't shrink anymore because it's already cool. And so it pulls the inside apart and puts the outside, squeezes the outside together. So now, remember everything above the line was compression, and everything below was tension. Now, the outside here is in compression, the inside is in tension. Does everybody kind of follow that?
What would this actually
until you reheat it, right?
Yeah, we're just leaving it there. We're letting it cool down to room temperature. What's that?
What kind of thing would come from this process?
Tempered glass. So have you ever noticed have you ever seen the behavior of tempered glass? Have you ever see a windshield from a car that's been shattered, right? All of a sudden you hit the windshield and tiny little pieces, right? The whole thing shatters into tiny little pieces. And if I were to, I'm assuming this is probably tempered glass. If I were to take a hammer and smack that, which I won't, because it's yep, tempered glass.
How can you tell?
Because it's written on it.
Well, if you taste the tempered glass, it has a slight iron taste.
Anyway, so you take, anytime that you've got something that somebody can walk into, it has to be tempered glass. So the reason you have tempered glass is because now the outside is in compression, the inside is in tension. So what does that mean? That means that if I bang on the glass a little bit, put a little bit of stress on the glass, right? The little crack at the surface is in compression. It's being squeezed. So my little bang on the glass isn't going to hurt that, isn't going to cause that crack to propagate. But as soon as that little crack extends that far, extends into that center tensile zone, all heck breaks loose, right? Because now that crack tip is under tension, it's going to go. And what's more, in order to drive that crack in there, I had to be really pulling apart on that outside, right? So I've got a ton of tensile force on the overall glass plate in order to get that crack to overcome the compressive force in the tempered glass and make it to the inside. So that huge force that I've got now is not just going to crack it there, but it's going to shatter it everywhere. And so when you're in a car accident and the tempered glass in your back window gets a ding, that ding fills the whole glass, and it's all little shards, right? All little tiny pieces. And that's why they use tempered glass, so that people aren't going to get, sliced by this big piece of, a big shard of glass jagging in the throat, right? Now your windshield, it turns out you can't use tempered glass in your windshield. Because your windshield would be breaking on a regular basis. Right? You get too much, you get too much for you, right? I mean, everybody's acoustics. We've all had a rock chip on our windshield, right? A little chip comes up and dings it, and then maybe a little crack grows out to the side, you know what I'm talking about? Right? Again, if that was tempered glass, as soon as that rock chip came out, boom, the whole thing would shatter and be useless. So the front window is not tempered glass, it's actually a sandwich of two pieces of glass with an elastomer layer in between. So that when the crack propagates, the elastic layer is there, the elastomer layer is there to keep it glued together, basically. So it doesn't come apart as shards. So that's why anybody go and beat on the van a couple weeks ago, you saw the guys, you were talking about. Yeah. So you take a sledgehammer to a windshield, right? The windshield doesn't go, right? In fact, you have to beat on it just to get the sledgehammer to go through the window. Because the whole purpose is to keep that all together so that it doesn't come into the passenger car. All right, so that's how tempered glass works. Does that answer your question, Joel?
Yeah.
All right.
So do you lose strength and toughness when you temper glass?
So
Seems like it'd be less strong.
Yeah, I don't know what the total behavior is, because it's I mean, you gain strength in the surface. The surface is stronger.
You gain strength on the surface?
Yeah, but
It's kinda like a
overall,
trade-off.
you know, it's a trade-off, exactly. You're focusing your strength in the surface where it really matters. Okay. All right, any other questions? All right then. So, no class on Friday. We'll go over questions on Monday, and then we'll take the test on Tuesday. At a time that you will arrange with me.
Is that also open book?
No,
Oh.
material science is not open book. Thermo is, material science is not. I will, yeah, I gotta do that. I gotta get you the, review of FE equation sheets for both classes. I'll get you those.
Just open office after 5.
Open office after 5.
Yeah, I'm gonna break into your office. We're gonna talk about that.
I already
That's
discussed
tempered
it.
glass? Your office?
It's tempered glass.
You'll find out, I guess.
Yeah, that's true.
I'm sure.
Oh, dude.
He'll never know.
Do you have, you gave us an email that has all the videos.